where we got started was mainly from our association with the theme park industry. It had come to us as a simple question. If we were starting from scratch, how would you build a safe autonomous platform? And the reason behind that is that, you know, Disney has even some patents. Everybody wants to do some kind of drone show, but legal shuts them down every time because they're not safe. So the first thing we had to do was define safe, but as we were thinking about it, the first conclusion that we came to was the obvious one. In order to make it safe, the first thing you have to do is get rid of the pilot. And everybody kind of nods and says, yeah, we get that. The second conclusion, however, is a lot less obvious, and that is you also have to get rid of the computer. And the reason for that is that general purpose computers, if you attack this problem from a software angle, general purpose computers are designed to do everything poorly. They will do everything, but the inevitable consequence of that flexibility is that they don't do any one thing particularly well. And so, just a second, trying to figure out how to, there we go, now we should be able to. Okay, so if we start from scratch and we want to make safe and autonomous world, if you will, platforms, what is it we're going to need? Okay, so we have to have some way to design the path that these vehicles are going to take without having humans required. You know, think of the FAA. You know, if we had to get an FAA flight plan approved for every time a drone needed to go out, it would simply never happen. But these tracks have to have enough leeway to avoid unforeseen obstacles, birds flying, balloons, kites, anything that might pop up. Most importantly, in my opinion, we have to find some way to mitigate the potential of using these vehicles to do harm. Right now, it's kind of the elephant is in the room, is that it is very easy to, you know, fly one of these things into a place where it shouldn't be, and do significant damage. And as soon as, you know, one of these yahoos with an AK-47 figures out that he can do this without putting himself at risk, the game is going to change rapidly and dramatically. Okay, so moving on, we have to increase the payload capacity and flight duration. You know, these battery-operated systems that currently tap out at about 38 minutes simply aren't going to make industrial applications. Finally, we have to be able to program these things. The reasoning is that in order to, you know, really open up the industrial market, we have to be able to create application-specific vehicles. Now, if we could solve any one of these problems, that would be pretty cool. But our goal is to solve all of them with one architecture. Oops. Okay, so the way we're going to do this is, since we've said we're not going to have a pilot and we're not going to have a computer, what we've got to do is we're going to build the entire autonomous architecture with hardware. And this is what's called a hardware accelerator. Basically what it is a supercomputer that is architected from the ground up to perform one task and perform it very, very well. So the layers are, first of all, what we call TRACKPATHs, and then secondly, the second level is a hardware navigator, and the third one is a hardware pilot. Now we break them up into these different tasks because this allows us to architect each layer specifically for the data and the processing requirements of that layer. And when we do it, each layer significantly simplifies the layer underneath it. And that's the key to making everything work. So at the TRACKPATH layer, basically this is kind of how we think about it. You know, instead of flying from point A to point B with what were called waypoints, we actually define the real-time path in a spline, for example, which is a mathematical expression of a curve or a line, but it's mathematical. So it can be interpreted at any degree of accuracy necessary. So instead of just saying, okay, here's point A and a mile away is point B, and you got to figure out everything in between. No, we're going to give you the exact path down to the millimeter that you're going to fly and the exact time that that's going to take. So all of the structures that we're talking about are true four-dimensional structures. Okay, so now to implement these, we've got our hardware accelerators. So the first one is our navigation supercomputer that we call Stevie, which is short for Safe Temporal Vector Interpolation Engine. So once we have the TRACKPATH, and the TRACKPATH basically tells it exactly what it's supposed to be, where it is, and where it's supposed to be going in any instant of time, all Stevie has to do is basically integrate these vectors. He simply has to know where I am and where I'm supposed to be in the next click of time, and he generates a vector to get from one to the other. Now, there's not quite that simple. There's a lot of vectors, but we'll get to that in a minute. But the point is that the mathematics of this now becomes relatively simple, and instead of turning out a fix, if you will, a vector from where I am and where I'm supposed to go, in most systems that is on the order of feet of accuracy. Thank you. Whereas with Stevie, it's now 1,000th of an inch. And if you're turning out these vectors every 1,000th of an inch, that accuracy and that speed changes everything. So, for example, if I were to do any kind of a change in a control system that causes undershoot, overshoot, oscillation, right? These are the standard things that happen in any control system. But if I'm dealing with things on the order of feet, those matter. If I'm dealing with things on the order of 1,000th of an inch, they really don't. So it greatly simplifies what we have to deal with. Okay, so if I'm turning out these vectors every 1,000th of an inch, basically when we come down to the piloting supercomputer, we call VIGO, vector in, guidance out, now his job is even simpler. He doesn't have to know where we're going. He doesn't have to know why we're going there. All he sees is I've got a vector that says I'm going to point myself upward and to the left at this angle, and all he has to do is make the platform do that. So his job actually now gets very simple as well. Okay, so here's a good shot of kind of what we see as the layered architecture. The first stop is the TRACKPATH. So we compute these paths automatically. We'll get to that in a second. The second part is that we compute these before we take off. We don't do this computation inside the platform. We pre-compute it based on where I want to go. So that's when I have all of the computing capability, all of the data that I might need. Literally, what I would need is a three-dimensional map of the world and a good-sized server farm. And gee, Google already has all that. Okay, and then finally we have the platform. So the platform is made up of a collection of essentially hardware supercomputers. Now, supercomputers used to look like the thing on the left. Now they're the size of a deck of cards. So we can do all this in a very small and easy to work with package. Okay, the interesting thing is that once we do that, once we solve this basic architecture challenge, then things start getting really interesting. So for example, let's look at what we're doing with this path planning. So what we have right now is there are two camps. This one's the Amazon avoidance model. And what Amazon's doing is they're saying, we're not going to pre-compute it. We're just going to tell the platform where it has to go, and it's got a really good collision avoidance system, so it will figure it out, and if something gets in the way, it'll move. That, you know, and they talk to each other and they do a lot of other things. But the simple problem is that you run afoul of what's akin to Newton's third law. Any action results in a reaction. If I see a platform headed my way on a collision course, I'm going to turn and alter my course. Okay, that's fine, but you have to realize that the other platform is going to do that as well. So now both of them are changing course to avoid, and that has a ripple effect. That's going to affect someone else now who will suddenly realize that they're now on a collision course. So this structure by itself ends up devolving into what we call the pachinko effect. Now, the other model is Google's, where they're cooperative. We pre-plan the track paths, and everybody follows their path, and everything is under control. Now, what Amazon complains about this model is that, and it's true, this simple model does not allow for something coming in the way that you didn't know about ahead of time. So a balloon, kite, a bird, a news helicopter, you have to be able to deal with those. And Google's model does not currently do it. So in our model, what we're saying is, yeah, you're both right. You have to have both of those things. So our track path structure from a data standpoint combines our four-dimensional navigation splines plus timing. It involves inverse geofencing, and the structure also gives us a programming language at the same time. So with those things together, it starts being a little bit interesting. So I don't know if you've ever seen auto routing, but if you've ever looked at a circuit board, they use auto routing to compute those. And I wrote three-dimensional auto routers for 15 years. There's not very many people actually in the world that understand auto routers. They're very tricky, very difficult, surprisingly difficult to design and build. So in our case, what we're going to do is we're now going to extend the auto routing paradigm into 4 dimensions. Nobody has ever tried to do this before. The patent space is completely open on this one, so this is one of our most valuable patents. Okay, so we start with a 3D image of the world, which Google already has. We basically overlay that with a grid and intersect the two, and that gives us basically a breakdown of where we can fly and where we can't fly. Okay, and by using this grid structure, that's our computational area. Okay, now what happens in 4 dimensions is that I want to fly through this area, but what we're doing is we're taking every other vehicle into account that has been granted a track path before us. So in this case, at a given time, the path that I want to take intersects with a path that somebody else is taking. The actual algorithm for this is called topological auto-routing by successive approximation of cellular morphology. Love that title. Now, but what that means is that these grids that you see are variable. They can be from 100 meters to centimeter to millimeter accuracy. And so that allows us very high computational power over very wide areas, but still we can get to the accuracy that's needed to thread this thing between power lines, for example. Okay, so I've got this collision. So what I do is I have 4 dimensions to work with. I can either turn left and avoid him, or I can simply delay my takeoff for 30 seconds, and he'll now move out of my way, and I've deconflicted. So having 4 degrees of freedom now to work with in my auto router really creates an interesting solution. Okay, so again, now you see why I need all of this computing power, because if I was the FAA, for example, I might be having to compute 10,000 of these track paths every hour, each taking everyone else into consideration. I don't want to be doing that calculation inside the platform. But what's really interesting is that you suddenly realize that we now have all of the skeleton of a true air traffic control system. just because we started off wanting to make it safe. Okay, so that's our 4D navigation and timing segment. Now let's look at geofencing. Right now, the only safety device that has been defined is called a geofence. Basically, you draw a circle around an airport and you can't go in that circle. There's only about 100 different ways that that can be defeated, including a highly complex system known as a piece of tinfoil. That's all it takes to defeat the geofencing system and, fly this thing in somebody's window. So in this case, the simple case is an inverse geofence. So in this picture, what you're looking at is, for instance, the inverse geofence for something like a lagoon show at a theme park. Now, instead of saying you can't fly into this area, you can't fly out of this area. That's the simple case. Now, where this, basically could be defined pretty much the way that a geofence is now. But in the next case, it gets a lot more interesting. The geofence is also a four-dimensional construct. So it changes over time given the relationship of it, of the platform and its path to the real world. So here it starts off being kind of a tube, and then around these skyscrapers, its allowable area gets smaller, and then out of the city, it gets larger again. So this kind of a construct can't be defined under the current geofencing paradigm. But this is what's necessary because, remember, one of our primary goals is to mitigate the ability to do harm. In this case, because the track path is generated, for example, by the FAA, that same autorouter is generating the inverse geofence, and now the platform simply cannot fly anywhere it's not approved to go. It can't leave this fence. And that's how, basically, you make the entire system safe at once. Okay, so you saw in the previous slide where it looks kind of like a tube. That is a three-dimensional projection of the four-dimensional reality. So at any given point in time, basically that tube, the keep in zone, looks like a sphere to the platform itself. So what this allows us to do, though, is because all of these auto-routing concepts are based on cost functions, we can now create these paths by all the things that the FAA wants to control. Well clear metrics, who's the pilot, what's the platform's capability. So these are reverse platform. All of that information can be fed into the free flight corridor objects as we define it. Okay, so the last thing then that we're going to do is programming language. Okay, so the purpose of this is solves a multitude of problems. One of them is anytime you've got a platform that's going to be flying on its own, it has to have some kind of contingencies. The TRACKPATH program itself is programmable. So, for instance, I have a scene analysis system and I have a tracking system. Why can't I use those to alter my programming? So instead of just flying, basically what we're doing is we're saying, okay, I can alter my TRACKPATH programming based on things that I'm analyzing in the environment around me. Now we have the basics that you need for basically being able to make intelligent decisions and make application-specific vehicles. Terminal avoidance is basically a second autopilot, if you will. And what it does is, if things go wrong, his job is to take over the platform and do whatever it takes to figure out how to land it or get it away from the people or do what's necessary to come down in a safe manner. So basically what we're saying is that drones that can fly are cool, but drones that are application programmable, that's how you make them useful. Think about, we haven't seen a paradigm like this since the early days of the personal computer. Yeah, they were interesting games, game machines and playthings when the Apple II first came out. It wasn't until, for instance, IBM and actual business applications started showing up that they really became useful tools. And we are looking at that exact same paradigm shift now. Right now, they're cool, they fly, you can put a camera on them, cool. But when you can do business applications, that's when they're going to take off. Okay, so in that, now the thing that it comes down to architecture again. If I want to do application programming in a software architecture machine, these CPUs, no matter how you program them with multiple tasks, they are still only doing one thing at a time. They simulate a multitasking environment, but they're not truly multitasking. So in order to do this, and people in the standard autonomy world, other companies are starting to talk about application programmability. But if you look at the architecture, you've got the CPU at the bottom. That CPU will have its own operating system, which is often humongous. Then you've got your flight application software that runs on top of that. Now you've got to add a flight operating system, and then finally you can write your platform application. Each layer of this exponentially increases the difficulty, debug, and speed. Exponentially decreases the speed of the overall application at the top. By contrast, hardware is naturally multitasking. That's why we build it in hardware. So you end up with pretty much what you expect. You've got the flight hardware, there'll be a flight OS on top of it, and then your platform application is running on top of that. So now you've essentially got the same end-of-the-day architecture that you have on your PC and everywhere else. And that is well proven. Okay, so back to what we were trying to do. High accuracy, cooperative vehicle tracking, no humans required. Check. We can do that. Enough leeway to avoid unforeseen obstacles. Inverse geofencing gives us that. Mitigate potential of doing harm. Inverse geofencing gives us that. Increase payload capacity. We're going to get to in a minute. And then user programmability to create vehicles. We can solve that. So, now that we've got that solved, what kind of things can we do with that? And that's where things get really interesting. So, for instance, all we have to do is add some way to monitor that, that airspace, and we have a complete air traffic control system. So we have one of our patents, for instance, is in the use of the existing national cellular infrastructure to monitor the airspace. That gives us low cost, high coverage, and critical warning, because now if we, what we are assuming is that we have simply an IFF transponder in the drone. Once we've got that, we can now tell the difference between the 200 guys that are going past us that are paying, that have transponders, they're doing what they're supposed to be, they're going to have TRACKPATHs, and the 2 guys that are flying by who don't. That means we can now enforce the regulations. And without enforcement, everything that the FAA is doing is completely, completely worthless, quite frankly. It's sort of like what freeways would look like if there were never any traffic cops. Most importantly, that gives us critical warning. In a high threat environment, or close to a high value target, we can now provide extra minutes of critical warning before an illegal vehicle is coming near. Okay, logistics is another really interesting area. Now, obviously, Amazon, Domino's Pizza, everybody wants to do drone delivery. And when I first saw that, I'm going, okay, why? Why go to all this trouble just to get it there 5 minutes faster? Well, it turns out that if you run the numbers, Amazon, for example, not Amazon, UPS pays its drivers, the last mile delivery scenario, $3.3 billion a year. Anything that you can do to shave a minute off their overall time saves you about $100 million a year. So logistics is not being driven because it's cool. It's being driven strictly by value, which is very good for us. So the other thing about logistics is that it's 90% of everything. If you look at, the Department of Defense, for example, only 10% of the Army is spent actually warfighting. The rest of it is spent in logistics. And so the same thing is true of almost every other business. Okay, so if we want to look at the delivery market, what we now have is the ability to provide a complete end-to-end solution. Our platform, Stevie, Vigo, TRACKPATHS, they don't care whether you're a three-dimensional flying vehicle or a two-dimensional wheeled vehicle. And for example, Tesla has announced that they're starting to work on autonomous 18-wheelers. So if you think of how we can deal with what's in between, the Amazon last mile model and everything else, what we've got now is a situation where from the time a package is put down to the time it's picked up at the other end of the country, no human ever touches it. Okay, so one of those things is by pickup locations. So those can be automated, those can be kiosk-based, or they can be, your backyard-based, depending on various issues. So in terms of, for instance, a retail kiosk, the basics of a retail kiosk were outlined in the early Amazon patent. But what they missed was, consider that I've got this kiosk, and I've got the ability for it to accept packages from a drone. And the reason you do it from the top is to keep people away from the whirling blades of death. And I can drop this off, and now I've got a drone with nothing in it that I've got to send somewhere else. Okay, so what you do is you just add in the fact that you can drop off a package at one of these kiosks, and when a drone comes in to drop off a package, it can now pick one up. And if it's going from one kiosk to another across town, it can go straight over there without ever having to go back to the main distribution hub. So now I've more than doubled the effectiveness of the system just by having two-way availability at the kiosk. And that's a patent that we have and Amazon does not. The other interesting thing is mail delivery. Nobody has gone after mail in the patent space, really, because it's a much more difficult problem than packages. But we've taken a look at it. This drawing is of what we call a drone pipe, which basically sits outside your home and is a place where basically it's your mailbox. You can actually even hang your normal mailbox on it. But its purpose is to accept drone delivery of little packets. And so, that's in there as well. Now, in terms of delivery, certainly there are short-range drone platforms. But it doesn't make sense, for example, to take, to have 5 packages flown 5 miles across town to the same area. What you need is a carrier, something that you can fill with boxes, fly it and your short delivery platforms across town, and then have it do the drop-off, and then they all fly back together. There are a whole slew of interesting applications where it takes more than one drone to complete the mission. And so we call those drone carriers or robotic carriers. And that's one of our patents as well. So, it works whether it's a land-based platform that you're driving across town and you're launching your drones from there, or you're doing it across town with another aerial vehicle. Finally, we basically identified that our platform doesn't care if it's a three-dimensional flying platform or a two-dimensional wheeled format, and in this case, it's a one-dimensional format. So this is an automated shelving system that basically reconfigures itself in cooperation with our 3D auto routing system, which is now, instead of working across town, is working inside a factory. So we have these little wheeled vehicles we call box trolls. Their job is simply to pick up a box, walk it over to another place and put it back down. The automated shelving systems allow it to drop it down there, and then they reconfigure. But the interesting part here is that the shelving systems don't require any space between them. No aisles. So with this simple architecture, basically we now have the ability to load and unload vehicles, store all of the boxes for intermediate as they go from one place to another, and we've increased the usable space by more than 100%. So if you implement, for example, the shelving system inside the truck body or inside the air shipping container, now you have a completely autonomous system where the box trolls can load, unload, move from one place to another, or move to the flight platform for last mile delivery. Okay, so finally, we now, we can also provide, personnel effectiveness applications. Everything from accident and crime scene documentation to inspection to movement monitoring, convoys and shipments. Those are all places where personnel effectiveness comes into play. And having drones and drone carriers allows us to effectively attack those applications. Okay, and so this is another version of the drone carrier. Okay, so military applications. Can't forget those. So let's just give an overview of a couple different things. Right now, actually, in terms of drone carriers, the closest patents are in the area of cluster munitions. So imagine that, you're dropping one of these cluster, your current cluster JDAM munitions out at 60,000 feet. It basically heads down, splits into some number of little cluster variations. But it has about 3 seconds overall to decide where it's going to do, steer itself there, and then explode. So, that's it. It's over. You go on and do another one. Now imagine if instead you dropped one of these fellas out, and instead of just falling down, it goes into a hover that's, say, 4,000 feet. Now the guys on the ground have the opportunity to say, my laser is pointed at a door. Would you please make that door go away? So it pops out a little door munition. It goes to where the laser is pointing, and it makes the door go away. Now he can ask for a room clearing device, which flies in where the door used to be, turns into the room on the right, wife and kids. No, turns into the room on the left, AK-47s. Make the AK-47s go away. So now they have the ability to direct munitions for an hour or more against any target, even beyond line of sight. And when we briefed one of our local senators on that one, his response was, you just changed the fundamental nature of urban warfare, right? And we said, yes, sir, we did. Okay, so this is what we kind of call our bird dog class. So this is automated close air support. So these guys are now basically following a troop all day long because they have the power to do that. They're looking at rooftops. They're looking around corners. They're looking in windows. They're basically going to be the first thing that's going to draw fire. And so being able to provide close air support all day long to foot patrols is going to be a very interesting discussion. Okay, law enforcement, border patrol, wildlife monitoring, all similar cases. Why build a fence that you can either, it has been proven, you can tunnel under or walk over, when you can patrol the border 24/7, and if somebody crosses it, you can follow them for the next 2 hours until the border patrol can actually get there. In this case, we're using a state trooper car as a drone carrier. When he does a stop, the drone can go to a complete 360, visualizing everyone in the car so that he has a threat assessment before he ever steps outside. Okay, so search and rescue, natural disaster recovery. We've been asked to help on a bid for this for the state of Florida. We have hurricanes that do blow in from time to time. And when that happens, roads are out, power's out, communications are out, everything's a mess. Okay, so what they've asked us to do is within an hour of the winds reaching a trigger level, we can fly in what is essentially a set of new first responder or cellular towers that can cover the area and provide both disaster relief, disaster imaging, and first responder communications support for that area. And we can't leave out the theme parks. That's where we got started. So in this case, what they want is, a starfighter and a Millennium Falcon that's going to, be shooting lasers and pyrotechnics and is going to fly over the edge of the crowd, hopefully. But in order to do this, we need power. So we're finally going to get to talk about power. Okay, so batteries are not going to do it. It's going to take liquid fuel. And in order to do that, what we want to do is build a jet turbine power system. Now, you're used to seeing these things hanging off the wings of a 747, but if you look at the pencil in the image, you get the idea of the actual size. Now, the problem is there's a factor called the Reynolds number for jet turbines. Jet turbines themselves are the most fuel-efficient motor that's been designed. A normal internal combustion engine might be 17% efficient. A jet turbine can be as high as 60%. The problem is that the smaller you make them, the more the Reynolds number kicks in and decreases the efficiency and the power available. That's why they're made 8 feet across for an airliner. The trick was finding the size that would give us the right efficiency levels, but still be small enough and light enough to fit in a platform. The other thing about jet turbines, the reason they're not used currently, is that they turn at about 100,000 RPM. So you can't really hook that to a directly coupled generator. Now again, the one you're looking at right now, blasts all the air out the back in order to create thrust like a standard jet engine. But what we want to do is we want to turn a generator. So all of the power goes into turning a shaft. Okay, but I can't couple the generator directly to this at 100,000 RPM, which means that I've got to put a transmission in, which now, again, makes it too heavy to work in the platform. So we're solving this problem a couple different ways. Come on. Oops. Went wrong way. Okay. So this is the actual turbine unit. You can get an idea of the size. And the big area on the left is the directly coupled generator. Okay, this is a high-efficiency lift motor that we are designing with a relatively clever new take on field theory. So this lift motor will be able to generate we're going to be using ducted fans instead of propellers for a little bit higher efficiency, and there's no whirling blades of death. So we've been working on this new type of motor, and basically as soon as that's done, which is relatively soon, we will be applying the same field theory to our generator. So those two things together will allow us to provide approximately 12 kilowatts of power to the platform and its payload with liquid fuel, which means we can basically make it run as long as we need to. Okay, So here's kind of a view of our patents. The green ones on the left are all about different applications, mostly around the drone carriers, mail delivery, aircraft, and entertainment. The ones in the center are ones that deal with airspace, so using the cellular infrastructure, having an IFF module, integrating with the FAA, four-dimensional auto routing, and the TRACKPATHs themselves. And then the ones on the right, the blue ones, are all about the platform itself, being able to use hardware instead of software. That single change, for example, is what gets us around the Amazon patents. Okay, so just to give you an idea of how they correspond, this is the patents that apply to air traffic control and the platform itself. These are the patents that are in the logistics space. These are in the overall air traffic space. This is a human flight capable system patent. And this one's for entertainment. So, proof of concepts. So we're currently on our 4th revision of our high efficiency motor, which will then turn around and become our high efficiency generator. We have completed our initial proof of concepts for TRACKPATHs, the hardware pilot navigator system, and we've done that through simulation so far. And now that we've completed the initial simulation, we will be starting much more rigorous, more accurate simulations. And that is where we are today in tech.